So today we're going to delve into the topics of dynamic processing, more specifically compressors, and we're going to look into gates. So dynamics, defined from Wikipedia. In music, the dynamics of a piece is a variation in loudness between the notes or phrases. Dynamics are indicated by specific musical notation, often in some detail. However, dynamic markings still require interpretation by the performer depending on the musical context. For instance, piano marking in one part of a piece might have a quite different objective loudness in another piece, or even a different section of the same piece. The execution of dynamics also extends beyond loudness to include changes in timbre and sometimes tempo rubato. So dynamics, when we're discussing in audio engineering, shares the same definition, but we kind of delve a little bit deeper into that. Very important to note that dynamics will change your timbre. We're going to talk about the differences, where the different ways we as audio engineers look at dynamics from our perspective. There are different dynamic tools we'll be working with. Compressors, limiters, expanders, duckers, and gates are probably the most common. Today we're going to be looking at specifically compressors and gates. And we'll discuss the difference of each, different parameters, certain applications you may use these for. So what is dynamic processing? In short, dynamic processing is the attenuation of a signal's dynamic range, or the softest to the loudest signal. So just like in the context of if you're playing a piece and we have dynamic markings, we discussed dynamics is essentially volume, or the dynamic range, the softest to the loudest signal. We use dynamic processing to shape, we'll call it the peaks and the valleys of a signal or a track, so these loudest points and the softest points. We can also use dynamic processing to shape the tone or timbre of a specific instrument. The most common dynamic processor you'll see is the compressor, which reduces the peak amplitude, also called downward compression, or we can make the soft passages louder, also known as upward compression. So when we're discussing gain and volume, this always relates to sound pressure level, and how we measure that sound pressure level is decibels. And this should be a little bit of a review from our first week. The decibels, abbreviated to dB, is a logarithmic unit, so this increases exponentially. We discussed adding 3 decibels doubles at amplitude's intensity, but we as humans don't perceive double the volume until an increase of 10 decibels. I've mentioned this before. A lot of what we do is manipulating audio to create a psychoacoustic effect. It's not necessarily about what's measured. Just because the sound pressure level is double, if we don't perceive that as twice as loud, it won't be twice as loud. Having these measurements in the back of your head as well will help you when we start digging into fundamental applications of compressors, of gates. We have the ability to visually see the gain reduction in decibels. So you can use a visual representation to help achieve what you're going for audibly. So what do we talk about when we're mixing, when we're working as audio engineers? What is the difference between dynamics, say, is dynamic markings in a score, piano and forte, versus most common level of dynamic processing? We can break up dynamics into 2 categories we'll call macro dynamics and micro dynamics. So macro dynamics would be a variation in level for a musical event longer than a single note. So macro dynamics would essentially be you playing your part, reading off a score, seeing the forte and piano, and this is a visualization of a waveform of a complete song. We can see the macro dynamics. It's softer in the beginning, there's a little crescendo, maybe a build up. We can see the thicker texture here. So that would be the macro dynamics. This is something to consider when working as a producer, an arranger, mastering engineer. Mixing though, a lot of what we're working with is what we call the micro dynamics, which would be the variation of an event within a single note. So this is also pulled from our first week when we discussed envelope, attack, decay, sustain, and release. So this would be the envelope of a single note. So envelope would be the collective measurement of the waveform's amplitude in relation to time. Again, a lot of what we're working with as engineers is dynamics over time. Your total cycles of peak and negative amplitudes within a specific time is your frequency. It gives us our notes, amplitude over time, gives us our envelope, which is a large portion of timbre. So a De-esser, attack measured from the initial hit of the instrument to its peak amplitude. So attack is very important. If you want to do some experimentations on your own, record some notes on an instrument, slice off the attack, and it's very hard, or manipulate the attack in some sort of way, and it becomes indistinguishable from other instruments. Decay time is that time between the peak amplitude to the initial sustain. The sustain is the level of the main sequence of sound, and the time it takes for the level sustain to run down to 0 dB, or that sound to completely diminish, would be the release. And you could say this is kind of a visualization down here of the envelopes of different sounds. A tuning fork will produce what's pretty close to a perfect sine wave. The flute has a little different attack. It wavers a little bit in the sustain. Characteristics of the human voice are going to be different. A violin's envelope is a little bit more squared off. And this, again, the envelope shapes the timbre of the sound. When we look to attenuate an overall performance, the overall levels, we're kind of looking at the macro dynamics. When we're looking to shape the instrument's envelope or the signal's envelope, we're looking into the micro dynamics. So compressors, we could now develop our foundation into our first dynamics tool, being the compressor. Your typical controls on a compressor: threshold, ratio, knee, attack, release, and makeup gain. There may be some variation. You may have things called key frequencies, input gain that affects the output, and the other controls. There are different types of compressors. Some may have less controls than this, especially in the digital domain. These would be your typical controls you would be able to manipulate, and we'll go through each of them, listen to sound samples of each, so you have an idea of what each control is actually doing to the sound, and go into each control a little bit in depth. So our first control we'll look at is the threshold. This is essentially the set point in which audio activates the compressor. We're going to set a threshold to a certain point. Any audio that passes that point, that threshold, will then in turn activate the compressor. It will be attenuated by the compressor. Anything below that certain threshold will be left alone. This selectively treats the audio by dividing it into two sections. Again, anything down here below the threshold is left alone, and you can see anything above this threshold right now, it's set to around, in this example, around minus 20 decibels, activates the compressor and is attenuated accordingly. When that input signal reaches the desired decibels set by the threshold, the dynamic processor is active. So again, we may have a guitar part playing down around here. It suddenly gets louder, reaches that decibel threshold. Instead of following this linear curve, this linear output, the compressor knocks it down. You can see I'm over here now. We're following this curve of the compressor. A lot of digital compressors will allow you to visualize a compression in a graph such as this. It's very easy to be able to see that. Not all of them. The compressor in the slide previous is more based off of an analog compressor, so it has VU meters, so we could see the amount of gain reduction. But again, a lot of digital compressors will show you a graph such as this. Let's listen to how the threshold affects an audio signal. We're going to first listen to the threshold dropping. So essentially, we're going to start a threshold, or we're going to have an unprocessed signal. We're going to start bringing the threshold down and down, so more and more of that signal is being processed and compressed. And then we're going to listen to that same curve dropping of the threshold, this time with compensation for the output. Now, going back to this again, you can already visually see that we're getting less output here after it's being compressed. So if we drop the threshold down, the actual signal is going to get a lot quieter. That's why we have this control over here, makeup gain. You see where my pointer's at? The makeup gain allows us to compensate for the loss of signal while we're compressing. So let's listen to these samples. So we can hear as the compressor started really clamping down on that signal, we lost a lot of the gain. The volume just dropped tremendously. We could also hear the timbral changes when the kit was over compressed. It started to almost sound distorted. The drums started to lose their natural feel. So now let's listen to the same threshold drop on the same signal, but this time the output volume is being compensated with that makeup gain. Next, we're going to look at the ratio. The ratio is just that. It's a level ratio between the input and output. Think of a water hose, and we're running water through a hose, and the opening on the input side is the same size as the output. You're going to get a certain ratio. Whatever water goes in, that same amount is going to come out. If we squeeze one end, maybe we have the size of the opening of this water hose, only about half of that water is going to come out. It's the same concept with the dynamic processor compressors ratio. So we define the ratio in terms of input to output. Over here, 1-to-1 input to output is unaffected. And that's translated in this white line here on this graphed out compressor. So again, if we were to follow it, we have the threshold set, but if there's no ratio above 1-to-1, the compressor is not going to affect your signal at all. And it goes up pretty intuitively. 2-to-1 ratio would be 1 dB of output for every 2 dB that's inputted to the compressor. So say a signal is jumping over your threshold about 10 dB and we have a 2-to-1 ratio, only 5 decibels will make it through that compressor. So you could see this output ratio for downward compression visualized in this graph. Again, the 1-to-1 would be unaffected. And it's, again, a great visual tool, especially as you're learning how these compressors operate. So let's listen to a rising ratio. This time the threshold is going to be set, and the ratio is going to continue to drop and drop and drop. So as you can imagine, if it starts at 1-to-1 and the ratio drops and drops and drops, we're also going to lose gain. The gain of the signal will be diminished. So again, we're going to then listen to this rising ratio with gain compensation. So first, here's the rising ratio. And rising ratio with gain. So very similar effect to the dropping threshold as well. The knee is essentially how fast the compressor clamps down after the signal surpasses that given threshold. We refer to knees as a hard or soft knee. A hard knee will trigger the compressor very quickly after that threshold is met, and a soft knee will trigger the compressor quite a bit slower. You can see this graph of a hard knee is visualized as a sharper angle versus a soft knee, which is a smoother onset. Depending on the attack, what you're trying to achieve with this, that's how you would choose your hard or soft knee. Some vintage compressors, even in the computer modeling domain, won't have this hard knee. We're going to look into attack and release after this. It's different. The knee is a little bit less important as the attack and release, but it's an extra tool you have to further fine-tune and manipulate your sound. So let's listen to that knee. Here's the original.
Who am I? running around in circles just to pass the time.
Here we have that vocal being compressed with a hard knee.
Who am I? Running around in circles just to pass the time.
And the same vocal compressed with a softer knee.
Who am I? Running around in circles just to pass the time.
Hopefully you're able to tell. If you couldn't pick up on it, I'd encourage you to rewind a little bit and listen. The hard knee resulted in kind of a more in-your-face vocal sound. With this soft knee, the onset was a little bit softer, kind of rounded out the vocals a little bit more, smoothed it out. Attack and release. This is going to be labeled in milliseconds, and that is the time it takes to activate the processing. Attack time is in milliseconds, and it's a time it takes to activate the processing. The release time is that time it takes to kind of let go of the signal, for the compressor to release the signal that is being ingested into the device. These are very often, especially with engineers who are learning this trade, learning this skill, often forgotten about, and attack and release times are really some of the more important controls you have on your compressor. These are what's going to squash your envelope, if it's going to open up your envelope. Depending on where you want to go with the signal, you may want to maintain that attack time in your signal's envelope. Again, we're going back to these micro dynamics now. This is how your sound is shaped. This is how it's either going to sound natural or unnatural. And you could see this visualization of an envelope. Here's the amplitude, your threshold. So everything above this threshold is going to be clamped down. You could see, however, the attack time set over here allows the envelope's attack to remain unaffected, and it only begins to clamp down on that initial decay. Psychoacoustically, by maintaining very loud attacks, compressing the rest of the envelope, the listener usually perceives that sound as louder, remains open, as opposed to if you were just to clamp down this attack time and leave that squash with everything out, that's when sounds start to sound overcompressed and muddy. A fast attack time will attenuate the attack of the envelope. Again, this may or may not be desirable. On this example, we're going to listen to the attack time on the snare, with ever increasing, starting at 1 millisecond, 10 milliseconds, 50 milliseconds, 100 milliseconds, then finally 1,000 milliseconds. 1 millisecond, obviously very fast. A lot of that snare attack is going to be squashed with the rest of the envelope. And you're going to see as we open up the attack time to allow more of that initial attack of the sound unaffected by the compressor, begins to sound more and more open. So that was 1 millisecond, moving on to 10. So we could already hear more of that attack opening up through the compressor. 50 milliseconds. So at 10 milliseconds, we heard the attack poking through the compressor. 50 milliseconds, we're letting more of that attack and maybe even some of that decay through the compressor. 100 milliseconds. Now we're starting to sound very, very natural. Less of the signals being compressed. And 1,000 milliseconds is letting most of that envelope through. In regards to especially the attack and release, but collectively additive through each parameter, we get these compressor artifacts called pumping. These are usually unwanted artifacts caused by very quick and noticeable levels of attenuation. Usually if the release is too slow or the attack isn't there, it's overcompressed, we get this pumping sort of effect. So we're going to listen to a drum groove again. First the original, then pumping with the fast release, pumping with a medium release, and pumping with a slow release. So here's the original. Next we'll have fast release. So you can hear the initial transients being let through from the drums. Then all of a sudden the overtones are diminished and the transients are let through again, and we get this pumping effect. Next we're going to have pumping with the medium release. And lastly, pumping with a slow release. So again, it's not natural sounding. Depending on the desired achievement, this may be useful. However, it's a common pitfall for a lot of engineers learning compression to overcompress, not notice. Really should pay attention to what your track sounds like with and without compression. Adjust the attack and release times accordingly. Be wary of not overcompressing. Breathing is another unwanted artifact from overcompression, not setting the controls properly, but this is usually associated with fluctuating noise level. So we discussed noise floor when we had our lecture on audio to digital conversion. If there's any noise, this example is going to be with a vocal. It might be more common with, say, a single coil electric guitar that inherently has noisy pickups, and overcompressing will bring up the noise.
Who am I? Running around in circles just to pass the time. I need to find my own direction in this life, a path on which our destinies unfold.
Here's an example for using pumping for kind of an added effect. I'm going to have you guys look this up on YouTube individually. Exit Music for a Film by Radiohead from the album OK Computer. This was mixed by Nigel Godrich. Again, look that up for YouTube. The drums come in around 2.5 minutes, and they use this pumping effect to add movement to the drums. They use it as an effect. So again, once you learn this stuff and know the rules, you can break the rules, just like in music theory. Know how to get these certain effects, know how to avoid them when you don't want them, and then you could use this as kind of a color on your palette to paint this picture when you're mixing. Pause this video for now, look that up, and we'll come back. The de-esser is a specific type of compressor used to treat sibilants. Again, S's in vocals tend to pop out at you at kind of annoying frequencies, maybe between 6K, 8K. Each voice is different. So this compressor is activated by a predefined key frequency. You can see this picture right here. We have around 7,155 hertz, around 7K. And when this threshold is set just 7K and some of its neighbor frequencies around that, once those frequencies surpass that threshold, only that narrow band of frequencies are compressed or knocked down a little bit. That way we could push up the vocal without having those frequencies be irritating to the listener. It's also kind of a form of band compression. You're going to hear, we're not going to get into it in this lecture, multi-band compression, where you might have 6 bands like that across the frequency spectrum to kind of attenuate the spectrum of what instrument, not just a top end, not just a sibilance, but the de-esser is definitely the most common form of band compression we have out there. So again, group of frequencies around 7K surpass that given threshold, those frequencies are attenuated. And lastly, we're going to talk about gates today. Gates are probably the second most common dynamic processor. They're sometimes called noise gates because you'll use them to suppress noise. In the listening example we heard of with the breathing effect, there was a very exaggerated, noisy vocal. There was some gating going on where when the gate opened up, it let in the noise. So this essentially works as kind of a reverse compressor. You could see this threshold is set over here in this depiction of a compressor, over here in this graph. Anything below that threshold is cut off or diminished. Once we surpass that threshold, it opens up to allow the signal to pass through. We use gates to remove unwanted noise like a hiss, hum, or rumbles below a certain threshold. So again, going back to the example of a noisy single coil guitar that usually always has some sort of ground hum. It's just a noisy guitar by nature. Sometimes even guitar amps, high gain amps, have gates on them to remove some of that noise. And once you start playing, it opens up. It lets everything through. Once the signal falls below that predefined threshold, it'll start chopping it off. And we have this extra control, the range, which is the amount it reduces. At that point, we're kind of getting into expanders, but it may not just completely chop everything off to 0. You could adjust the range so everything's attenuated, maybe 20 dB, etc. A very, very common use of gates is when we're close miking a drum set. And we'd use gates on the individual drums to reduce bleed from the other drums being captured by other mics. Maybe lower drums, like low toms, floor toms, might end up with this rumble or ringing caused by other drums, and you could use gates to remove that and clean up your mix quite a bit. Let's listen to some gates. This is going to be some drum recordings. Again, we're going to listen to the original. Then the threshold set at minus 40 dB, minus 30 dB, minus 20 dB, and minus 10 dB. So again, let's take a look at this again. It might be hard to see, but you'll notice minus 40 dB way down here. The threshold's so low, most of that signal is going to be passed through unaffected. So once we start raising the threshold, it's going to start affecting the signal and chopping it off. Again, kind of works in the opposite way of a compressor, where lowering the threshold of a compressor is going to affect your signal more, where in gates, lowering the threshold of a gate will actually affect your signal less. So here's the original. And we're listening to this snare microphone. So the gate is going to attempt to try to remove all that unwanted bleed from the other drums around it. So it was with the threshold set to minus 40, and you could hear it was largely unaffected. There were certain parts where there was some brief attenuation with the background noise. But again, once we start backing off on the threshold, we're going to hear this snare affected more and more. Here's with the threshold set to 30 dB. So now we have a lot of that background noise now is starting to be attenuated and chopped off. Here's with the threshold set to minus 20 dB. So we're really starting to hear that snare become more and more isolated. Here it is with the threshold set to minus 10 dB. Now the snare is pretty isolated. You hear the instruments going in and out, but again, we're close miking each of those drums, so that's going to cover up any oddities with that. Gating, not only does it help isolate the channel, it helps reducing any issues with phase cancellation as well. And lastly, we're going to talk about gated reverbs. A few weeks ago, we had our lecture on reverbs, briefly discussed what gated reverbs were then. I want to revisit that because now we have a firm grasp of reverbs as well as gates. So gated reverbs, it's kind of it's a processing technique that combines a strong reverb with gates. This was discovered by a producer named Steve Lillywhite when recording drums for Peter Gabriel. This is usually used as an effect to thicken drums, although Phil Collins famously used it on his vocals for many solo albums. Think of the quintessential 80s drum sound, 80s drum snares, these big gated reverbs. This technique is still used even with modern productions. It's a little bit more subtle. It thickens the drum sound. It helps extend the drum note or the snare hit into the next beat. It really gives you this defined, strong, solid drum sound. So we're going to listen to a few examples of that right now. So first, I want you to pay attention to the snares and the toms. First, we're going to do drums only. Then we're going to have drums with reverb only. Next, we're going to use drums with compressed reverb, drums with compressed gated reverb, and drums with uncompressed gated reverb, so you guys can hear the difference of this. So again, first, drums only. So good drum recording. Sounds a little bit dry, very isolated. So let's check out drums with reverb only. So we added some sort of digital space with that reverb. However, reverbs tend to muddy things up quite a bit if they're not tame. If you notice, the reverb tail was trailing off into the next drum hits, which, depending on how thick or sparse your arrangement is, could be a little bit of an issue. It also sounds kind of like a weak reverb, especially if we're working with hard-hitting drums. So let's listen to what drums with compressed reverb sound like. Definitely a lot thicker of a reverb, but we have even a bigger problem with that tail of the reverb smearing the next drum hit going into the next beat or the next note. So let's hear what compressed gated reverbs sound like. Good, so now we still have a really thick reverb, but it goes away in time to make room for the next hit. Obviously, this would be exaggerated. It would be mixed in a little bit more, and with instruments adding layers over on top of the drums, even that level of gated reverb isn't going to be as noticeable, and it adds to the drum sound itself. Lastly, we'll listen to drums with uncompressed gated reverb. So the reverb's a little bit more subtle. It's a little bit more natural sounding. Even with that gate, it allows time for the next drum hit to enter. So that is it for this series of compression dynamic effects videos. I'm going to be posting a video on creating aux channels in Pro Tools and setting up a gated reverb, a compressed gated reverb, how you would go about doing that in your own session.